Good morning, this is Dr. Turner for Integrated Math 3. Today we're going to be talking about section 2.3, which is graphing cubic functions. Just like in 2.2 when we talked about graphing quadratic functions, there are a lot of techniques that are expected to be achieved already that were taught in Integrated Math 1 and Integrated Math 2. So while some of these things will be very brief that I'm covering today, you may want to go back and look at the Integrated Math 1 or 2 videos to refresh your memory. 2.3 is looking at graphing cubic functions, and the heavy emphasis on graphing these functions really is going to come from being able to just identify key features and what a graph should look like. We're not really harboring on exact formulas here, and you'll see what I mean in just a second. So first off, what does a cubic function look like? So if we type in, let's say f of x equals x cubed, this is our cubic parent function, and you can kind of see the general shape of the graph. This can change once we add in, x squared terms or x terms, etc. But there are some properties I want to be familiar with a cubic function. The first of which is just this general shape. And I'm going to type in an example here. Just this general shape, and we'll use x cubed plus 2x squared as an example, where you have this curve that kind of goes up and then back down. That's not the same as with quadratic functions, for instance. So if I look at something that's quadratic, I have that parabolic shape or that U shape. Looking here, we should also notice that looking at the parabola here, we have the axis of symmetry, which we covered in 2.2. So in quadratic functions, we find that the parabola is going to be symmetrical about a line. And if it's a parent function that hasn't been shifted, it is symmetrical about the y-axis. So if I look on the left of the side of the y-axis or the right side of the y-axis, that's going to be the case as well. What we notice as we get into higher polynomial functions, whether it's something that's x to the 4th power or something that's x to the 6th power, for instance, we see that those same properties apply. And these will look a little differently if we add in other terms other than the quartic term and the hexagon term, for instance here. But for all of these, we notice that the graph is going to be symmetric across the y-axis. So all of these functions where the highest power is x squared or x to the 4th or x to the 6th, if my leading coefficient has an exponent that is even, we call that an even function. Going back to our example with our cubic function, these are not symmetric about the x-axis, but there is some similarity right around a certain point. So what we notice is that if we look at a cubic function, it is symmetric about the origin. And that's going to be true for any function that is an odd power, whether it's linear, whether it's something that's x to the 5th power, so on and so forth. So in this section, you're asked to be able to talk about different properties of odd and even functions. For odd functions, you need to know that they're symmetric about the origin, and for even functions, you need to know that they're symmetric about the y-axis. So those are sort of one of the things that you need to know. Also, because 2.5 is going to be talking about shifting different types of functions, you want to know what happens when your leading coefficient changes. So notice the general shape of my cubic function here. And if I change the leading coefficient to be negative, it flips. That's true if it's cubic. That's true if it's quadratic. Right? By changing the leading coefficient to be a negative, it flips it upside down, or it's reflected. So in this section also, you'll be asked that. What happens if you have a positive leading coefficient? Well, then it's facing up. And what happens when you have a negative leading coefficient? Well, then it's facing down. That's true for cubic as well as any other functions. Also with cubic functions, we see certain patterns that will occur if we change the coefficients here. So the standard formula for a cubic function is ax cubed plus bx squared plus cx plus d. If you're using Desmos, you can add sliders to the function and kind of just play and see what happens if I change one or the other. B and C will kind of change the shape of the curve, if you will, but the most common questions that you'll be asked are regarding the leading coefficient and the constant, so the a and the d. And this is true with cubic functions as well as any other function. So if I look at the a coefficient and I increase it, notice how the graph is getting more steep. That's because whatever number is in front of that x cubed, it's being multiplied after the exponent's been applied. So it narrows your graph. Whereas if I decrease a, let's say something that is less than 1, but still positive, it makes the graph wider. So as a is decreased, it's going to make the graph more wide, or a horizontal stretch. And if a is increased, then it gets more narrow, which is a horizontal compression. The d, the constant here, and this is true for any function, whether it's cubic or otherwise, the higher d is, it shifts the graph up, and the smaller d is, it shifts the graph down. So d moves the graph up and down, a makes the graph wider or more narrow, and if it's negative, remember that it'll flip. Another thing you're asked to do in this section is to be able to write a possible equation for a given cubic function. The reason I say possible is because there are a few different techniques that you could use to get different answers. But the thing that we want to focus on when we're looking at cubic functions is that we have a positive or negative coefficient and want to be able to identify the zeros. Just like with quadratic functions, the zeros are where my graph is crossing the x-axis. So if I can identify those points, then I can come up with a possible solution or possible equation for that graph. So if I look here in this example, I have a 0 at -2, -1, and 3. So those 3 points are zeros that I can use to create an equation here. Remember that when we write the 0 in factored form, just like with a quadratic equation, we want to pay attention to signs, because if you remember from quadratic equations, our formula was x minus r1 times x minus r2, where r1 and r2 were the zeros. So it's going to be a similar process here. When I go to write a possible equation for this cubic function, one possible scenario where I don't have an a value is going to be x minus a -2, or x plus 2, times x minus a -1, or x plus 1, times x minus 3. So this is one possible equation for this function. Some texts will ask you to write it out in expanded form. Others say it's okay to leave in factored form. If you were to do this, this goes back to integrated math 2, where you're multiplying polynomials. But just as a review, because I have 2 terms by 2 terms by 2 terms, before I simplify, I should have a total of 8. So let's say they asked me to do this in expanded form. I would do x times x times x, and then x times -3, and then x times 1 times x times 1 times -3, 2 times x, 2 times x times -3, running out of room here, and then 2 times 1 times x, and 2 times 1 times -3. Then, just like in Math 2, we want to identify any like terms. So all my x squareds, all my x's, and then combine. So this would be x cubed. The x squareds will cancel out here. I have -3x minus 6x plus 2x, so -7x, and then minus 6. Let's look at one more example of this. Here we have another example. If you are using Desmos to graph, sometimes you have to zoom in, zoom out, kind of get an image of the picture. Remember that you can also always go to the settings bar here. And because my domain is so narrow, I could go in here and say change the x-axis to be from -10 to +10. And it just, again, this kind of stretches it out in a way that I can identify what I'm looking for. In doing that here, now I can see a little more clearly the zeros, which are at -5, -4, and +3. So if I was asked to write a possible equation for this, I would start out, I have x plus 5 times x plus 4 times x minus 3, and then multiply those any number of techniques. We talked about this when we covered multiplying polynomials. You might choose to multiply 2 together first and then multiply the third, which is fine. So if I do that here, x times x, 5 times x, 4 times x, and then 5 times 4. And then I have a binomial times a trinomial here. Again, I could use distribution. I could use the box method if that's the preferred method of choice. But x squared times x squared times minus 3, 9x times x, 9x times minus 3, and then 20 times x, and 20 times minus 3. Combine all my like terms, I have x cubed minus 6x squared plus 6x squared minus 7x and minus 60. So this is one possible solution for this equation. We touched on this a little bit here when we were doing these examples. Some equations, or some problems rather, are just going to ask you to identify the zeros of a function. Because we're doing this online, really if you have your Desmos up, you don't really need to do the arithmetics, as it were. We're going to be talking about that as we get into later units when we're talking about dividing polynomials, which is going to be its whole other thing. It's a strategy that we're going to use quite frequently. But let's say I just gave you an equation, x cubed plus 4x squared, for instance. I could ask you to just identify the zeros. Now, if I'm not graphing, if I just had the equation, that's a whole nother process. We're going to talk about how to do that using long division, synthetic division, other factoring techniques. But because we're using Desmos and we're specifically talking about graphing, if you use your graphing utility and it says identify the zeros, you're just going to tell me what those zeros are. So in this case, if I asked you for the zeros, you would tell me -4, 0 and 0, 0. Remember that a polynomial can have up to as many zeros as its degree. So if it's cubic, it can have up to 3. Now in this example I just gave, there were only 2. But if I do something, let's say -4, for instance, well then I have 3 points. In our examples, because we're doing this online, I'm giving you examples where you're going to have an integer as a 0. But it doesn't mean it always is. It could be a fraction, it could be a decimal, just like it is here. Your technique when identifying them using Desmos is to just graph it, type it in, and then tell me what are the zeros of the function. Well, that's it for today, guys. If you have any questions, please reach out to me. And otherwise, have a good day, and I'll talk to you soon.